Welcome back everyone to the lecture about applied bioimage analysis. This part will be about 3D image visualization, but also a bit processing in Python using scikit-image, ITK, and Napari. So if you want to open an image, three-dimensional image in Python, it is as simple as it was in 2 dimensions. So you use scikit-image, you use the imRead function to open your TIFF image, and then here I'm printing out the shape, and the shape is basically the dimensions of this image. So it has 111 planes, and in X and Y, actually in Y and X, it's 1024 times 512 pixels wise. So it's the Drosophila dataset from the folder where also the slides are. And if you then want to visualize this image with matplotlib, you get an error message. Simply because viewing 3D images in a flat 2D browser is hard. There are ways to deal with that. Starting from our loaded image, you can actually do something like that. I mean, if you look at it in a 3-dimensional image with dimensions like that, it is actually just an array of an array of an array of pixels. So if we kind of look into the first dimension of this array, so for example, we look at the first 2-dimensional array in our 3-dimensional array, or if we look at the 25th or the 50th and so on, we get these individual planes from our dataset. So what I'm doing here in code is basically moving the bar from the left to the right in ImageJ in order to see individual planes. So this is how you can do these very simple operations with matplotlib. Furthermore, you can also do maximum projections, in this case with numpy, so numpy.max. And you enter your image and you enter an axis. And that's actually pretty cool because the maximum projection in Z, so this is the maximum projection in Z. Maximum projection in Z from ImageJ we know already, but the maximum projection in Y and X is actually quite hard and not hard at all in Python. So you can just do this, right? So that's actually pretty nice. Furthermore, what we may see here already is, at least the one who is used to looking at Drosophila datasets, it is supposed to be circular in this dimension, and I would actually expect that in the X dimension, the image looks very similar to this one. So obviously, it's not taking the pixel size into account, and that's why we see it kind of with the wrong aspect ratio. And in order to fix that, you should first start with some variables where you have your pixel size, and from that you can calculate the aspect. And the aspect is a parameter of the imshow function I haven't shown earlier. And as we are now executing the same code again and again, I'm collecting this code in a function. So I have here now a show xyz projection function, which does the same thing as just one slide before. It does a maximum projection of the image along z. It does a maximum projection of the image along y. And it does a maximum projection of the image along x. And I enter the aspect of the visualization to get these images out. And this is how it's supposed to look like. It's actually quite easy to use. Nevertheless, you may want to put these blocks of code into a function, put this function in a separate Python file, and then just call it when you want to, for example, show an XYZ projection of your particular image. As you may realize, visualizing things in 3D is actually quite hard in the browser. So quite some people suffered from that. And that's why I started developing tools to make these things easier. One group of people who wanted to deliver 3-dimensional image processing to Python and also 3-dimensional image visualization is the people behind the Inside Segmentation and Registration Toolkit, ITK. Conda install ITK brings another package, not much to talk about. And with ITK, you can process medical images. So ITK has a long history in development. It's a software library which is quite old and is for the medical imaging field. So you may find some operations and some things which are unusual for microscopy data, but very usual in medical imaging. And on the other way around, you may not find some operations which are very practical for microscopy data, but in medical imaging, nobody does it. So CT data, MRI data, maybe you want to process that with ITK. When you go to the website, also here, you find a lot of examples explaining you how to use these tools. I will give you a very short tour. You say import ITK, And then from ITK, you can, for example, use the imread function to define it. So the developers of the ITK Python bridge try to make everything as convenient as possible for people who are used to processing images in Python already, for example, using scikit-image. They try to make everything as similar as possible. Nevertheless, there are significant differences between these libraries. And one difference is that, for example, if you print the image out, it is not a numpy array. It is a special data structure. This special data structure contains a lot of important information. For example, it contains the spacing of the dataset already. That's very useful, keeping the data, describing the image, the metadata, and the image together in one structure. So that's why you have this kind of complex data structure here, and in medical imaging, it's really necessary to deal with certain problems. And you can then, for example, read out the pixel spacing like that. So when you say image.getSpacing, you get whatever this thing might be. It's a vector, but at the end, it's a collection. So you can access it like any other collection. You can say image get spacing, and then here in rectangular bracket 0, you can put the results in a variable, print the variable, and you know the voxel size is 0.8 in the Z dimension. Furthermore, ITK brings tons of filters. It's really many. You just call them. It's also very similar to other processing libraries. You just say itk.media and image filter. They hand over the image and you hand over the radius, like in ImageJ, for example. So it is as convenient as possible to get a median filtered image out. Furthermore, when you're in the Jupyter Notebook, you type itk dot and then you hit the tab key, and then it will give you a very long pull down with all the operations which are there in ITK, like the maximum filter, not to mix up with the maximum intensity projection I introduced to you today, mean filter, median filter. So there's a lot of operations there with similar parameters like above. So it is actually quite simple to use. And furthermore, if you want to convert such an ITK image, so I showed you it's a different data structure, right? If you want to convert it to numpy, you have to call this function array view from image. So without going too much into detail, you get a numpy array back, and you can then visualize this numpy array. So here you see again the MRI dataset of my head, shown with numpy, loaded via ITK, processed with a median filter in order to get rid of the noise you may have seen earlier. And then ITK, the ITK developers, I think it's a very recent development, came up with ITK widgets. And here you see already, this is a Jupyter notebook. So on their website, you see a Jupyter notebook, which is visualizing a three-dimensional dataset in the browser, which is pretty cool. But I must also mention it's under development. So it's like not a fully featured software, which has a history of 30 years like ImageJ. So this is a thing which is under development, which is cool, which is also nice and easy to use, but it may change in the future. So what you do, you import ITK widgets. From ITK widgets, you import view, and then you can just view the image. And this may work nicely if you have isotropic voxels. In our case, the Drosophila dataset is then again wrongly visualized because of the anisotropic voxel size. So you have to import the image into an ITK image. This is the other way around. And then you can set the spacing to the voxel size we defined in the other Jupyter notebook, and then you can view the ITK image, and it will then give you the correct three-dimensional visualization, again, in the browser, which I find pretty cool. And you can change brightness, contrast. In medical imaging, usually they do not change minimum and maximum intensity like we are used to in ImageJ. People in medical imaging change the window width and the window center of the gray value space, which is shown. And that's actually quite neat when it comes to three-dimensional image visualization in the browser. Yeah, if you want to learn more about ITK is, I would say, advanced developer stuff. So I would not say that everybody who can do a little bit scripting should dive into this, but if programming is your thing, then and your image processing is your thing, then ITK might be a good resource to look at. There's so many algorithms published in medical imaging using ITK that the ITK people at some point started their own journal. So it's a website where algorithms are published, and usually you can download the C++ or the Python source code for these tools which use ITK in order to process, again, usually medical images. So after this short excursion to medical imaging, let's go back to microscopy and life sciences and image processing. So you may have heard that Fiji software, that there is also an island called Fiji. So apparently software developers in this field like giving island names to their software. So there were some developers, some of them were sitting in Melbourne, some others in San Francisco, and they wanted to make a new software for the Python environment, and they were looking at the map between them, and you find, when you zoom in there in this particular region, you find Fiji Islands, and you also find Napari Island. So, and then that's why they call their new software, which they are making now, Napari. And Napari is a multi-dimensional image viewer for Python. I would say it's not by chance that Fiji Islands and Napari are so close to each other, because when you see what you can do with Napari and when you think about Fiji, they are actually very close by each other. So when you go to the Napari website, you see first of all this, and you can then already scroll down. You see some simple example code, and you see that this is apparently an image viewer, and a very powerful one. I would like to guide you a little bit through. In order to initialize Napari, that it works in your Jupyter notebook or in your Python code, you first of all have to start with import Napari, and then you should run Napari graphical user interface Qt. You can alternatively use this one. I'm not sure in which situation which is better, but maybe the one doesn't work, and that's why you want to try the other one. And then afterwards, you can create an empty Napari viewer with napari.viewer function. It will open a window like that. And in order to show a window in there, you just say viewer.addImage. So if you remember, I introduced object-oriented programming last time. So this is apparently something like a class. So it's an abstract representation of a viewer. Then on this viewer, which is kind of initialized here, on this viewer, you can call operations, for example, for adding an image to the viewer. And then it will actually look like this. And furthermore, so there's a lot of buttons. You can change brightness, contrast up here. You can also change the lookup table, which is now called a color map. You can also play a bit with interpolation operations and other stuff. I also would like to raise your point to this button down there, because it activates the 3D view of your three-dimensional dataset. So that allows you to get a view like this. So here is already the hint. Napari is obviously not thought as a 2D viewer like ImageJ was initially, and then somebody built in three-dimensional functionality. Napari is a three-dimensional viewer, which by chance also allows you to visualize two-dimensional data. So the rationale behind Napari was actually to start as a 3D viewer and build in tools which are necessary for processing three-dimensional image data. So when you rotate your view in Napari, you see the same issue. Also here, the voxel size was not set, and that's why the aspect ratio of our dataset is not visualized correctly. So we have to fix that. In order to fix that, you can, for example, call code like this and remove all images which were there in Napari already. So with a little for loop, we go through all the layers in our viewer. So the layer L is now the variable, and then we can say, viewer, please, the layers of the viewer, please remove this particular layer. So this is how you read this code. If there is just one, it's trivial. But maybe you want to clean up your viewer at some point and reuse it for something else, then this might be a cool piece of code. Then afterwards, we can add a new image, and we have another parameter here now. So it's again viewer.addImage, like earlier, with an image parameter. And I added another parameter for adding this scale here. And in our Jupyter notebook, which you also find next to the slides, you find also this variable here. And then we can inspect the dataset in 3D. So the mouse wheel is for zooming in and out. With the mouse button, you can actually nicely rotate this sample in 3D and get a view on it. It's very convenient. Then you can add more images. So for example, if we use scikit-image to do some background subtraction, and we want to add the background subtracted image to the same viewer, you see then here, you have then here entries for every layer which was added to the viewer. And you can toggle them on and off by clicking this I button here. That helps you to compare the original image and the background subtracted image, for example. And again, you can change brightness, contrast, and so on up there in this box. The idea of the Napari developers was maybe they used ImageJ before and they were very annoyed by all these windows popping up all the time. And they wanted to have that differently. And it is actually quite convenient to have everything in the same coordinate system in one single window where you can just turn off and on layers. So that's the concept here. Not having a lot of windows floating around on your screen, having one window and then turning on and off layers. So this is basically the hint here. And furthermore, layers can have images. So you see here I have an image layer. I have a background subtracted layer. That's the image you saw earlier. I also have a blurred image because I was doing some spot detection, find maxima. And I see the peaks here. I see them twice. I'm not sure why. So here you see how the local maxima detection in scikit-image works. And then I add this to the viewer with the add points function. And before doing this, just a hint here, if you want to try that out yourself, print out how many points there are. If you're adding something like 27 billion points to Napari, Napari may not be responsive anymore. And then you can go through your data set and you see the spots on top. And this is some kind of functionality we always wanted to have in ImageJ, and it was super hard to bring there. Some people are working on stuff like that, but in Napari it's obviously very convenient and very easy to handle to show some spot detection results, annotations on a three-dimensional data set. Okay, without going further into Napari. So also Napari is under development. The developers have a huge momentum, so there's a lot of things happening in a short time. There is tutorials online. You find another YouTube video also from the New Bias Academy, where Nicola Sofrino was showing in detail how to use it. When you use it, please cite it so that these developers also continue having funding in the future. So one thing I learned, and some people asked in one of the Zoom seminars, I learned it during using Napari. So so far we were creating Conda environments by creating a new environment and then installing software into this. And I told you that you can exchange Conda environments with other people so that they have the same software installed as you. And for example, if they want to allow us to try out Napari on our computer, they want to provide an environment where there is Napari installed. And this is the so-called environment YML files you find in some example repositories of example code for Napari. And when you look into such a file, you will see this environment, this Conda environment, is defined with a name Napari and with some dependencies. So for example, a scikit-image is necessary, JupyterLab is necessary, a TIFF file to open TIFF files. And they also define a channel, that's the Conda Forge channel, which is activated by default anyway, for defining where these packages online can be found. You can create a new environment on your computer like the environment on somebody else's computer by getting this environment file from the other computer. So you can get a professional environment file like this and install it, and it looks actually like the normal installation, the normal creation of a new environment. You can also export an environment yourself by using this command. I would just hint you, after you exported your environment, have a look at this text file. It's good for documentation to know which particular version exactly was necessary in order to run the tools, the analysis you did. But before you give this to a collaborator, you may want to clean it up. So it's different to the exported environment I just showed on the slide before. So, but this is the way how you can automatically, with a command line tool, export an environment and hand it over to someone who wants to reproduce your analysis, who wants to run your Jupyter notebook at their computer. Okay, that brings us to the exercises for today. First of all, install in ImageJ these plugins. So the ImageJ 3D suite, the 3D script image science is a toolbox for image processing in very general, which is needed by the 3D ImageJ suite. And also give morpholibj a try, because there are also many three-dimensional operations in there. And then process the Drosophila dataset in the folder provided. When I was playing with this dataset, I figured out that it takes a long time in 3D, and I don't want to waste your day. So that's why I would recommend do it in 2D and try to remember the steps which were necessary, which we had at the very beginning of the semester. You want to do some noise removal first, you want to do some background subtraction, You may want to do thresholding and particle analysis afterwards, and then have a visualization like that. And it may take some time in 2D already to figure out a good workflow, because this data set is actually quite hard to process, and that's why maybe you don't go 3D. But if you want to try, I showed you the most important steps in order to also process this data set in 3D. Furthermore, use Napari 3D script ImageJ to visualize this data set in a good way. So, and try to get a bit of feeling about what is actually a good visualization of such a data set. So that's basically a playing exercise. And last but not least, so that you can actually have some experience with three-dimensional processing, I would recommend you with activating the stack histogram checkbox in the thresholding dialog of ImageJ. You can actually process three-dimensional images. So the histogram for determining the threshold for segmenting this Drosophila embryo is determined from the whole stack. And then you can get one binary image out where the embryo is segmented, and you can load this one in the 3D ROI manager, the 3D manager, and do a measurement. So just so that you get a bit of feeling about the 3D manager and how to deal with ROI. So that's like one big ROI you want to take a measurement from. But it's actually quite convenient to play with the 3D manager. There are some optional exercises. So one optional exercise which may be fun, maybe not, fly through my nose in the MRI dataset provided with the slides. And you can also, if you like, take the tribolium morphometry example script of CLIJ. So there's a CLIJ example script which allows you to do this processing on the graphics card in something like 5 seconds. And it's not slow. That's why I'm recommending it here. It is super fast. So download this example. First of all, try to make it run on your computer, and then replace some code in there so that it does not process the tribolium dataset anymore, but the Drosophila dataset. These datasets are very similar. So this exercise is actually not a programming exercise. You should not write a whole workflow. It's more about understanding a given workflow. You download it somewhere from the internet and trying to figure out what you have to change in order to apply this workflow, which was programmed for tribolium, on a Drosophila dataset. So taking software from somebody else, reading and understanding it, and then applying it to your own data is a very common task in image analysis. That's why you can practice it here. That's an optional exercise again, right? You have to change something like 3 or 4 lines of code, not more. So when you find yourself writing 10 lines of code, it's already too much. Furthermore, I give you a hint. There is a Gaussian blur step when processing the tribolium dataset, and I would recommend replacing it by a difference of Gaussian. And we can later in the Zoom meeting discuss why we are doing that, what is the difference of Gaussian in this context. So looking forward to this. That's it for this week. I introduced you to some mostly visualization tools for three-dimensional data, but I also showed you roughly how to process images in 3D. It is basically the same operations in 2D. It's just one parameter more for the radius in Z, for example. And it takes a lot longer in order to process these operations. So three-dimensional image processing is harder just because the data is larger. Next week, we will go one step further. We will have a look at 4 and 5-dimensional data. And then we again have to actually think about how to get actually a view on our data. So I will, for example, introduce you to the cylinder maximum projection, and I will show you what the cumograph is. See you next week.